Looking good. Okay. So atomic and molecular structure, that's chapter 1. And what we're going to be talking about is, this is more like a review of the previous stuff you would have learned in general chemistry. But in some ways, I'm going to teach in a slightly different way, and I'm going to kind of bridge into some of the stuff I'm going to be talking about. Okay? So organic chemistry is going to be the branch of chemistry that involves the organic compounds. Organic compounds are typically considered things that have a very limited set of molecules. Typically, it's the ones that are going to be carbon-based molecules, but sometimes it's expanded out to carbon, nitrogen, oxygen. Okay? And so these are organic molecules over here, but they include things like DNA, urea, etc. Okay, you'll notice that really almost all of the molecules that are biologically related are organic molecules. Okay. In the 1700s, organic compounds were defined as compounds obtained from living organisms. Inorganic compounds were defined as compounds that come from everything else, so not from living organisms. Okay, and this is probably the more widely used definition. However, it's not the only definition. Please note this is a completely different definition than the food, organic food. Okay. All food would be organic food, according to this definition, right? Yeah. Very different definitions. In fact, many things that would not be food would be organic in this case. So why carbon? So carbon atoms can form 4 covalent bonds to other atoms, and so they make incredibly great branching atoms. Okay? You can make an incredibly large number of structures, because it's kind of like, why do Legos work? Well, it's because their geometry allows them to work, right? Why carbon atoms? Because the geometry allows it. Right? And carbon atoms can link together in chains of almost any length, branch chains as well as straight chains, so you can even have rings. And so here we can see some bunch of examples. This is a branch chain right here of carbon atoms. We don't really care what's on the end of these other things. It could be more carbons. It could be hydrogens. We don't care right now. Okay. This right here is just a straight chain. This one has double and triple bonds in it. Is everybody comfortable with that so far? Okay. Note that carbon can actually make single, double, and triple bonds. Okay. It cannot make quadruple bonds. That's not the thing. Silicon. Well, you may look at your periodic table and go, hey, Dr. Clausen, how about the rest of that family? See, under carbon, there is silicon, isn't there? So, again, silicon would be found just under carbon on the periodic table. You'd expect most of the same properties to be true. And, there's a lot of the properties that is true. Silicon can do a lot of things carbon can. There's some truth to that. But it cannot make all the same structures as carbon, and it's a lot less prevalent in nature. So there's actually a lot of good reasons why carbon just is the one that works, whereas silicon is not. Probably the biggest reason, however, is just pure stability. Okay? Silicon bonds are just less stable, right? And so they break apart easier, and they don't exist as long. Okay? Carbon bonds, on the other hand, are just more stable, right? And so carbon structures are about 50% more stable than a similar silicon structure would be. And that's by far and away the largest reason for this, okay? It's just pure stability. And you already knew that, in fact. So as you look at the periodic table, what happens when you go down? Yeah. They're more metallic, right? They tend to make weaker bonds. They tend to not hold on to their electrons as well. You knew it. There's going to be almost all the things I'm going to teach you this semester you already kind of knew. You just didn't formally recognize it. You didn't make the connections. Okay? And in reality, there's probably about 80% of chemistry. You already know it. You've lived your entire life in chemistry. Like, you know this stuff. You just don't realize that you know it because you've never really thought through it, right? So whenever you're having one of those chemistry moments, going, oh my God, chemistry's so hard. Just step back and remember, you know this stuff. You've lived this your entire life, okay? This is everything around you all the time has always been chemistry. You know it. You just formally need to understand it now, okay? Like, relate it to something in your life, okay? Okay. So let's kind of entertain this idea of silicon atoms replacing carbon atoms in like a biomolecule. So right here we have a biomolecule. Does anybody know what that is? Glucose. Very good. Yeah. That's a sugar glucose, right? It doesn't technically have to be glucose. There's a few other sugars it could be, but yeah, let's say glucose. Because that by far the most common, right? So this would be silicon-based glucose, right? So let's say we had that glucose right there, right? So when we oxidize that glucose, how would that look versus a carbon-based one? Yeah. This is not a gas, is it? Oh my God, you imagine? Your basic metabolism produces a solid that you then have to figure out how to dissolve and get out of there. And this is silicon dioxide. Like silicates, the mineral, like this. You'd have those developing in your cells. Now, interestingly enough, this would be still an exothermic reaction that is pushed forward because it's separating into different phases. It's not as nice as this because gas is a heck of a lot easier to get rid of and infuse, right? But, wow, right? Wouldn't that change the dynamic of every pathway? It would be a heck of a change, huh? Plants would have a much different cycle of life, wouldn't they? No CO2. They have to grow on little mineral deposits. Chop them up. So, like, this chemistry really matters, right? Yeah. Everything about this just completely changes every aspect of life, everything you know. So let's talk about atomic structures and ground state of electron configurations. So here, what do we have? By the way, this is a Socratic method of teaching. It's much more effective when you think about things, even if you don't necessarily answer them. Try to think about them and answer them in your head, even if you're looking at a video. Okay, like pause and give it some thought. I do really like it. Really helps me if you do try to answer though. Otherwise, this is so much less fun for everyone involved. Okay, so what's that? So the whole thing's an atom, but what's this gray thing in the middle? Nucleus. Very good. Okay, and so nucleus or individual pieces would be nucleons, right? What are the parts of that? Protons and neutrons. Very good. White is proton, gray is neutron in here. What's the neutron charge? 0. What's the weight? Approximately 1. Yeah, that's actually AMU being the units is actually a carbon nucleus divided by 12 is the AMU. Okay. So it's approximately 1. They're not actually 1 for almost any nucleus except for, I mean, even in carbon, they're not 1 each. So, but the proton, mass 1 again, right? And then what's the charge? Positive, proton, right? Positive. Positive 1, because again, that's where charge comes from, right? Okay. What's this stuff here? Why is it like shaded and what's going on? It's an electron cloud. Why is it a cloud? Exactly. Not just move, they actually pop into and out of existence. So they literally don't even move between the space between. They literally, it's here, pop, and then it's over here. Okay? And it's really weird, and it is what it is. Okay? That's quantum, by the way. That tells you that. And why it tails off here is you're most likely to find this is probabilities of finding electron. Okay? And so your probability of finding electron is very high here. It's very dark, right? Your probability of finding electron out here is very low. And so it lightens a lot. Okay? And that same probability actually tells you the charge distribution as well. Because your electrons are negatively charged. They're about 1/10,000th the mass of one of these protons. They have almost no mass. And that's why they pop in and out of existence all over the place. It's also why they're out here roaming around, right? Because you're not roaming around and flicking everywhere yourself, are you? But your hair is flicking around a lot more, isn't it? And that's because it's lighter, right? And so if you have something 1/10,000th the weight, it's really light and can get moved around a lot by basically everything, right? And so electrons. Note that the empty space here, this is not an accurate representation of an atom by any means. Okay? Has everybody seen the football field? Okay. If you put a tennis ball in the middle of the football field, that would be the nucleus, the tennis ball. And then this first shell, no, not past the first shell, just the first shell, would be the end zones. Okay? That's how little of the space is occupied by that nucleus. It is absolutely minuscule. Okay? And then these electrons, they don't occupy any real space either, do they? So you are 99.99 something percent empty space. Okay? You are far more empty space than you are space. So if you averaged out your space, you'd be zero. But so this is what a nucleus looks like. You want to sort of keep that in mind because in reality, nothing's touching each other. It's all electric fields interacting, right? When we're talking about nuclei, okay? It's all probabilities of electrons finding electrons in a space. It's not actually they're there. And these electron clouds or orbitals, they're again probabilities of finding electrons. They're the space the electrons would occupy. They're not the electrons themselves. Okay? Okay. And I think I'm actually past now, aren't I? Okay. Yeah, please let me know when I go past because I will and have lectured like an hour and a half past. Yes. My analytical chemistry, like 4 or 5 years ago, I had 5 people in it, and I lectured an hour and a half past the time, and nobody told me. Because I don't have clocks. Yeah. This one I do have a clock, I guess, but it's off in the side. Yeah, they were fully into the lecture. I guess it was a good lecture because I was like, I guess just let me go on. They're like, no, it's good. we didn't have anywhere we needed to be, so.